got her PhD at CITA in Trieste, and then he moved to Princeton.
I'm a she.
She. Oh, she.
I thought he was a good friend.
Yeah, so apparently I don't know.
Exactly.
She did her first postdoc at Princeton, and now she is working and she is doing a postdoc at Rutgers. And she has worked on many different stuff from dark energy and modified gravity and the universe relates to CMB. And now she is going to tell us about how we understand the SDG.
Well, thank you very much for the introduction, and it's a real pleasure for me to be here and see some familiar faces, meet some new faces. So yeah, most of the work I'll be talking about today will be related to some work I've done trying to understand the spectral energy distribution of galaxies a little better. Most of it is work I've done in collaboration with these people at Rutgers, Acquaviva, with my current supervisor. Carlos Varga was my undergraduate student and just defended his senior honors thesis, so I'm particularly proud of this achievement. Michelle White, former graduate student with us, now taught at Stockholm, and Stephen Bickert, my friend and collaborators at Princeton. But we're also part of like a bigger group of people, and for me, as Amir said, I work in different fields, so I started looking in galaxies only a couple of years ago, and these people have been really, really nice to me, and they never called me immediate, no matter what kind of questions I would ask, and so I'm always very grateful to them for all that. Okay, so understanding the spectral energy distribution of galaxies seems like a big thing. I should say what I mean, and what I mean for the rest of the talk when I say big words like that. So the idea here is that you go out at the telescope, actually no, yeah, you, in the sense of, I would never do that. And you take these beautiful pictures, and like, okay, there are these galaxies. You actually, when you do drop that photometer, which is mostly related to my work, you take usually observation in different filters. And so what you actually have is a collection of fluxes. How many photons have you counted at different wavelengths? But what we actually would like to know about these galaxies is what their physical properties are. Things like, you know, how old they are, how much mass there is in there, what's their star formation history, are they forming gas, are they forming stars, are they quiescent, do they contain lots of dust, how far away they are, and so on. And the process of going from one to the other can be done by means of the spectral energy distribution theory. So for me, I'm going to like refer to the process in which we go from these to these. How do we do it? Well, again, let me say the problem. You want the physical problems, physical properties, you have the fluxes. And actually, it's a little bit of a cheat because you don't just want the fluxes. You need another ingredient. You need to have some models which tells you that for theoretical galaxies whose properties are known, you kind of think that you know how each spectrum would look like. So if you actually have these two things, after the initial phase where you puzzle, you may just decide to try different type of models, and you can try a model like the red one, which as you can see doesn't really work very well. You keep trying, you try a model like the blue, again, you know, it's a little bit better, but still not perfect. And finally, as you keep trying, you may find a model like the black one. And the black one is actually a pretty good fit to your data. And because you know the properties of the models, you can conclude that the data have similar properties, and you're done. So to say things a little bit better, I would like to identify with you 3 questions that we like to answer when we think about SCD fitting. First question is, how do I tell whether a model resembles the data? In this case of the black model, we did it by visual inspection, but of course when you have many models to try, this is quite impractical. Question 2 is, how do you pick the models? In general, you would like to spend more time picking models like the black one that works with respect to the red one that doesn't work at all. And finally, perhaps most important, how do you compute the uncertainties? How confident will you be once you find a model like the black that you find a model that is more or less right? And again, let's step it up just a little bit to promote the conversation in identifying what are the goals and needs of RCD fitting. So in general, what we actually need or would like to do is to build a so-called probability distribution function. This basically identifies specifies formally your degree of belief that a certain parameter will lie in a certain interval with a certain confidence. And you want to do this, say, respecting four basic rules. You want to extract maximal information. So once you've gone out and taken the data, you want to make the best out of it, right? You want to evaluate your uncertainties accurately. You want to avoid making assumptions a priori on what the shape of this probability distribution fraction will be. And you want to be efficient, which is another way to say that you want to work as little as possible. So in terms of how, this is something that I've been thinking about since I've been a writer for quite a bit of time. And what I did for that is to write the first publicly available Markov chain multi-calculator for spectral energy distribution. It is called galaxies. And there were reasons. I heard that every time that you do something, you should have means, motivations, and opportunities. So somehow I got to this point after working on different things because, as some of you know, I have like several years of experience working with CMB data, and in particular I have worked with CosmC, which I don't know what I'm talking about. So the Markov chain multi-calculator is widely used in cosmology. I thought that this was a field where something like this was particularly needed because many people were just working with grid-based models in which you build a grid and you build reference models, reference SCPs for a limited number of templates, and then you look at the one which is closest, and that's going to be your reference. But of course, it has a number of disadvantages that I will describe. And finally, I just had the opportunity to write this because I was looking for something like new and exciting to do, and there were people there who were studying galaxies pretty actively, and so I think that we had a good thing. And as I said, this is a tool that is publicly available. It's been so for, I guess, almost a year now, and I had some pretty good feedback that has really helped me improve it a little bit, and I hope to keep working on this for a while. So I'd like to describe it to you just to tell you what this code can do. And the first part, and this is what I like to call the GAL, part of galaxy, is the one that is related to issue number 1. How do I tell you whether the model resembles the data? And this is done quite simply by looking at the chi-square of the model. Of course, this is something that all of you are familiar with. So I can construct a likelihood, and this likelihood will be a function of the parameter, so where in parameter space I am. And in this case, what appears here is some quantities which are the easy ones. They are related to the observation. Of course, they're only easy because typically somebody hands me a file that tells you these are your measurements and these are your observational errors. And then I guess for me the challenge is how to build the theoretical flux in a certain wavelength that corresponds to the parameters, to this vector of parameters. And so to do that, you start from theoretical spectra that comes from so-called stellar population synthesis models. If somebody here has worked with galaxy, you might be familiar with these Persona-Chauleau models, which are widely used in the field. And what I did is optimize their publicly available code to build the spectrum of the galaxies as a function of age, of mass, and methodological. And in blue, I tried to put the things that I've done, and they're somehow new with respect to what was available. Then once you have that, you want to convolve these models with a certain star formation history for galaxies. And again, things that people think about are the so-called simple stellar population. There's just one barsec at a given time. Constant star formation history, and exponentially declining or increasing. You have nebular emission. This is actually quite important. We think that nebular emission is only important in young stellar population, which are very active. But actually, according to what the star formation history is, this can be also important in older sort of galaxies. You correct for dust. Dust changes the emission of light in the galaxy, of course, taking light from the ultraviolet and optical rain and re-emitting the infrared, as you know. You can add the second stellar population, if you so desire, and then you place the galaxy at the right direction. You correct the absorption from the intergalactic medium, you move it to the observed frame, you dim, this is like what distance does to your fluxes, and you multiply by the filter transmission. Finally, what you obtain is a flux density, which is the thing that enters the light loop here. And so this is, this chain of events is what this code will do for you. And even if they seem complicated, I always like to remind people that because you're trying to do a very difficult thing, you're trying to do to your theoretical spectrum what nature did to these galaxies in billions of years. And so each and every one of these steps contains a really strong approximation. We think that more or less we are doing something that makes sense. But of course, when you take something as complicated as a galaxy, and you say, okay, I just can apply a formula, and this describes how dust is affecting this galaxy. These are all like, you're inserting sources of systematic errors that it's really easy to forget about. And so I think I always try to tell myself, yeah, you're thinking that you're taking into account all these things. But really, every one of these is a simplification. And then the other part of this problem is the MC part of Latin C, which is how you explore the parameter space. And to explain this, I like to just take a step back. I have said that one of the things that we want to do is to reconstruct the probability distribution function, which is in general something that is in many dimensions, right? As many dimensions as the number of parameters that you're considering. But actually, it's not really that you need to know that probability distribution. What you want to do is you want to be able to do algebra on that. So often what people want are these so-called marginalized constraints, something that tells you, okay, at my 68% confidence limit is using that. And actually marginalizing is just a fancy word for integrating. So for example, if I have a two-dimensional PDF that looks like that, and I want to say, okay, but what is the marginalized constraint in this direction? Then I want to integrate in the direction that goes in and out of the screen. And this is quite different than just like projecting what I have without taking into account of how much volume there is in this direction. Now, this difference doesn't count a lot when you have a Gaussian, or in any case, a very regular probability distribution. But if you have something like a giraffe, for example, well, in this case, you have that the highest peak, what you would call the best, the one with the highest likelihood is here, with the head of the giraffe is. But the body has a lot of volume, so when you integrate, you actually get something quite different. So, similar thing, when you want to say, okay, what is like the expectation value of certain parameters, this means that you're in general computing the mean of a certain function, and the mean of this function will be computed integrating over all the dimensions that you have, so all of the number of parameters. So in general, doing integrals in many dimensions, which is, as a matter of fact, what you need to do, is something that is quite time-consuming. However, if you imagine having a series of points, and each point is here a vector in parameter space, that has this simple property, they are identically distributed to the probability distribution function, then if you're able to build up, the integral that we're talking about becomes just a sum of the value of the function that you want to evaluate on this series of points. And this is the essence of MCMC, which is nothing but a prescription to create that series of points. Here is what we call a chain, that has a nice properties of being distributed identically to the probability distribution function. How do we deal with it? Well, the idea is that you want to explore a parameter space, you want to do more or less randomly, because you want to go somewhere, but it's kind of like a biased random walk, where the bias is that you spend more time, you visit more frequently locations where the likelihood is higher. It was just a simple rule, so it's a line of code, and it's a very simple rule. But the idea is that if you do that, then you obtain these desirable properties, that the density of points that you visit is proportional to the PDF. And so any integral that you need to compute, whether it is to find an expectation value, whether it is to find a confidence region, just becomes a sum over the set of points. And this is also, by the way, a way, like we can look back at what MCMC means. So Markov is any process where the next step only depends on where you are. The chain, as we said, is this succession of steps. And Monte Carlo is any process that involves random numbers. Okay, now in the practical we show why it is convenient to use something like that. The idea, the alternative, usually, is to use a grid. So to compute the references at a different point and then see where you are. However, in this case, the point is supposed to use like parameter 1 and this parameter 2. So this could be, for example, the age of the galaxy, and this could be the mass of the galaxy. And a priori, you don't know, you need to allow for a fairly wide range of possible values for that. But the interesting region, meaning the region where the data and the model more or less localize, is typically going to occupy a very small fraction of this volume. And this is like truer and truer as for bigger parameter space, as you increase the number of dimensions. So if you build the grid, basically you're doomed to spend a lot of time computing the spectrum in regions where nothing interesting is happening. And also, of course, this scales really quickly with the number of templates that you have in each dimension. However, if you do it as in the MCMC way, you start somewhere in the parameter space and you start going around, keep going, and when you finally find the interesting region, which means left and right, when you get somewhere around this point, well, you basically keep something there and there and there. So you keep spending time in the region that you're interested in, even if a priori you hadn't known where that was. Just because at this point you realize, oh, my likelihood has gone down. This means that this is a really good fit to the data. I want to spend time jumping around here. And the things that I put here is something, in general, these algorithms are supposed to work. And if you have an infinite amount of time, they will always converge. But of course, there are things that you can do to make them a little bit more efficient. And in some cases, using an adaptive proposal density and using a proposal density, a way of jumping around, that is similar to the covariance matrix of your data computed on the steps on the chain is actually something that can happen. Finally, the last issue that I have talked about, and perhaps the most important one, is how to compute the uncertainties on these parameters. And again, you can assume that your probability distribution expansion is a Gaussian. And in this case, your 68–95% confidence levels are what we call 1 and 2 sigma deviations in a Gaussian curve. But in general, this is wrong. And I understand that here we have lots of cosmologies. This was for me one of the biggest surprises, one of the things that changed when you move from the field of cosmology and CMB type of things to the fields of galaxies. In case, most of the CMB physics is that at the time early enough, and many processes are linear. And the linearity and Gaussianity often go together. When you study galaxies, galaxies are messy systems. And so this is actually something that is fairly safe to do in the field of the CMB for what I've seen, but in the field of galaxies it can be very, very dangerous. There are many parameters in which the likelihood is really not Gaussian. And the other thing that you can do is just to integrate the probability distribution in many dimensions, and you find a contours which includes a certain fraction, like the desired fraction of the volume. And this is, of course, correct, but it's sort of painful. Or you can use these nice properties on the CMC. Because the density of the points that you're visiting is actually proportional to the probability distribution itself, well, this just becomes a big matter of counting points and finding the contours that include 68 or 95% of the total points that we have visited. This factor has no assumption, and most of all is very, very easy to do. So I don't think that MCMC, it's a superior statistical technique for any reason in particular, but the fact that it makes this type of calculation actually really painless.
But then can't you go wrong because if you have, for example, in some points the right button, so you'll get the wrong confidence because 7% of the
I'm not sure I understand.
So,
if you didn't explore the parameter space, there was another peak.
or vice versa, that you started far away, so you still have many points where it's not an interesting target, you get it wrong.
That is true. Well, I mean, when you start far away, this is like, somehow you always have to wait for the change to get to an equilibrium point. This is what we call the burning-in phase. And so, in general, what we want to do is to discard the initial path that is not supposed to be part of the chain. And empirically, the way that you test that is that you can say, okay, for example, if I discard the first 20 or the first 30% of the points, do I get the same result? If yes, then it means that you've done that appropriately. Your issue of the other peak is actually what I'm going to talk about next. So, computing is one thing, but how do I trust that the encirclements are correct? And this is, I think, the tricky point as many people who work in this field. So the problem here is that we know that we have the correct result from a mathematical point of view if we know that these samples, these chains, are distributed like the probability distribution function. However, there exists no sufficient condition to ensure that this property is actually verified. We have necessary conditions, so we can do as many as reasonable tests as we can. We'll never have a guarantee. So one thing that we could do is do this convergence test. So the idea here is that, first of all, if I take a chain and I keep running, are my results changing or not? If not, then that's a good sign. Second, I can actually start many different chains in different points of parameter space. If they all converge to the same place, then this is another very good sign. It is very likely that I converge to the correct result. So for example, if there are multiple peaks in the probability distribution function, this approach will guarantee that I actually find them. However, and so in general, running several chains starting in various locations is a good practice. However, the problem here is that, at least what I found empirically, is that if you have two peaks, these two peaks are adjacent. If it's something like that, and you run different chains, then I think it is fairly likely, it's fairly safe to assume that once the chains get in this region, they will explore these two peaks, and it will still be true that the density of the location that you visit is going to be proportional to the probability distribution. In other words, it will be true that the volume enclosed here and here is proportional to the respective densities. But if you have solutions which are far away, then I think you cannot trust, at least with MCMC does, to the simpler algorithms. And unfortunately, when we talk about galaxies, this happens fairly frequently, and depends a lot on what kind of data you have. There are data that will allow you to break this degeneracy and so exclude this one or this one. But if you find evidence of something like that, and if you run several chains, you actually will find this evidence, then what I would say is just you cannot trust your confidence limits. You should keep in mind that this is a possibility. All right. I think we have talked about methodology so far. Let's see if we can talk a little bit about science. So one of the categories of galaxies that I have applied this code to is this galaxy called Lyman alpha emitters. So Lyman alpha emitters are galaxies that, as the name itself suggests, they are bright in Lyman alpha. The Lyman alpha line is actually very strong emission lines. So these galaxies are easy to find. The way that we find them is that we identify the Flaxinen emission line as an excess in the narrow band that corresponds to the wavelength of that certain emission line at a given redshift with respect to the continuum. So you need a way to estimate the flux in the narrow band and a way to estimate the flux in the continuum, and this you do with raw methodology. So it is very easy to single them out. However, these galaxies are actually faint in the continuum, and so it's very difficult. Even if finding them is easy, then when you go and use broadband photometry and say you take images of these galaxies in multiple runs and then you want to do a fitting, well, usually these fluxes are pretty low. And so it's very easy to to study individual objects. And so what people have been doing is oftentimes to stack their fluxes. So basically to add them all together, and you know what happens when you add different fluxes that correspond to different objects. The signal goes down linearly, the noise goes up with the square root, and so you increase the signal to noise. So this is something that we did for initial sample of about 116 and a half liters, or roughly 3 in the extended chamber field cell. And this study in particular, this is in 2008, had considered them and segregated gas according to whether or not they were detected in the infrared IRAC band at 3.6 micron. So we had a bunch of them that corresponds to the red best frequency there, which are luminous, or relatively luminous in the infrared, and a bunch of them that are actually not detected in the infrared. And the first thing that we did is like, okay, we have that sample, that is a well-studied sample. We have this new algorithm that contains some improved modeling. So for example, we had updated templates and we had added nebular emission. We're going to look also at methodologicals, and we would like somehow compare what we obtained from our study of the full probability distribution versus sort of like the best fit and these like 1-2 sigma contours. And I think it's always good when you are applying something new to apply to something that is relatively well known. And this was the type of results that we got. So in blue and black, you see these two populations, the one that were detected and the one that were undetected in the 3.6 micron band. And we knew that some of them were younger, some of them were older. Most of them are consistent with being essentially dust-free, which is somehow not very surprising because the lamina alkaline is very easily quenched, so if there are dust scattered around, it never gets new. So that's important. And we were able to put a constraint on metallicity. It was the first time that this was possible for broad delta boundary only. Now, if you ask me, do you really trust this result? This is where the systematic errors that I was talking about comes in. We only had a few templates of spectra for a few values of metallicity. So there is an interpolation problem, and there is the fact that we know a lot about stars at solar metallicity, but we don't know that much about stars with very low or very high metallicity. So, we should keep it in mind that this is like, yeah, it's a great result, it's interesting, it's consistent with what people find from spectroscopy, but I don't think that we have the theoretical instinct to really trust what we're seeing. And this is the two-dimensional contours that tells you how joint distribution of parameters look like. And so this is one case, for example, in which we find evidence of a second peak. But in this case, because they are not very far away, I actually think that this is quite trustworthy. And again, if the probability distribution was Gaussian, this seems to look like ellipses. So it is, it's for the blue ones, it's actually a pretty decent approximation. For the black one, and this is just the nature of the data, the black data has less signal to noise, and so you see how you have much stronger deviation and have this bimodality that you actually cannot resolve.
So
yes.
For the bimodal distribution like that, how do you decide that it is too far?
I would say, well, here you see that the 95 confidence contours is actually joint form, and so I think that this is okay. And actually, what I found is that in all the chains that I ran, I find most of the probability here and a little bit here. So these are things that I tend to trust. But I think in the end, it's still a bit more of a matter of gut feeling. And this is, of course, less than satisfactory because ideally you want to have a black box. And when you have many objects, you need a black box. You cannot look at it galaxy by galaxy and decide whether you trust it or not. So I think it's an issue to work about. Another thing that I always like to share is what the impact of the assumption that you make in modeling the stellar population is. So in this case, we did the following exercise. We took one of these two samples, and the results from the 2008 paper is these like vertical lines, kind of the best fit with an error bar. And we started from using assumptions which were as similar as possible as the one used in this paper, which means it's Brusson-Sherlock 2003 models, solar metallicity and non-angular emission. And we changed these assumptions one at a time. And each of these four sets of assumptions is something that today would be considered completely reasonable. Not many people model nebular emission. We tend to think that it's only important for young stellar population. The difference between solar metallicity and the cryptosolar is really not that much. And stellar population templates, people, the jury is really still out on whether this or this work better. And still, if you look at the difference in the values of stellar masses that you estimate, you see that there is a factor of 3. And I think that this really tells you what is the main problem that we have in this field of SCP fitting. Our models are just not good enough right now, so that if somebody is saying, okay, I measure mass to 20%, well, that's one type of error. Then there is the error that comes from the modeling, which is, I think, the one. We need, I think, good algorithms, because we need to be able to separate what comes from the models and what comes from the data. I think this, each of these curves shows you how much error there is in the data for a certain set of assumptions that you make in a model. And you can reverse engineer, you can use that, and you can use the data to reduce the scattering. But I think this is something really important, and I haven't seen it mentioned too much. All right, another sort of interesting science result that we obtained a bit more recently was the following. So far I've talked about Lyman alpha emitters and redshift 3. Actually, most have taken Lyman alpha emitters and redshift 2. These two epochs are not particularly far away. There's only 1 giga-year between the two of them. Now, different people have studied the clustering of Lyman alpha emitters. And so they like to put the results on a plot like this. There's redshift here and bias factor here. This tells you how much your galaxy cluster, right? To do this exercise for Lyman alpha emitters, redshift 2 and 3, which are the 2 green points here, you see that, and these are tracks that tells you, okay, here I'm following halos that host galaxies of similar mass, and I'm following them to their cosmic evolution. And you see that basically this tells us that Lyman alpha emitters are redshift 3 and redshift 2 are hosted in halos that could evolve into each other. So it is kind of tempting to say, okay, so are these the same galaxies? Are these galaxies just evolving into each other? Or not? And you would say, okay, because there are so many people working in this field, just because LAEs are easy to find, sure, somebody must have looked at this particular problem. So I've actually did a search in the literature, and you see that, for example, redshift 5.7, this paper in 2007 found that LAEs were old and massive. Another author, same year, the median ratio of 5.5, found that they were young and small. Doing the same, redshift 4.7, young and small LAEs, same author, different sample, same redshift, we found them to be massive and dusty. Only 2010 found them that LAEs at redshift 3.7 were young and small. And at the redshift 3.1 were also young and small. That was encouraging. Unfortunately, Nielsen in 2007 found that they were all in intermediate mass. And the study that I just presented found that some of them were young and small, some of them were old and more massive. And then this author at redshift 2.2 found that we were young and massive. My collaborating with my student Lucia found that they were young, bursting, and intermediate mass at redshift 2.1. And you see that even if you just focus on this 5 result, which is the evolution from redshift 3 to redshift 2, this is far from a coherent picture. Now, what did we think that we could do something better than that? Well, first of all, because we had samples, redshift 3 and redshift 2, which have the same luminosity limit. And here, when I say same luminosity limits, I mean after adjusting for the difference in the difference luminosity distance of the two ratios. So it's really luminosity, it's not brightness. And this is important, otherwise you cannot, of course, compare apple to apple, which is a problem that you have when you look in the literature. And second, because we could use actually the same algorithm, because we thought that we could at least evaluate the impact of some of the sorts of systematic errors to the modeling, we thought that we could separate the errors that you make just because, okay, I'm using two different templates and things like that, from the actual evolution of the superpopulation of galaxies as this direction. Okay, so we went back to the photometry, redshift 3 and redshift 2, and we started from the images, and we made sure that also the way that we built the stacks were actually exactly the same, and we did median stacking, and for redshift, median stacking is more robust to outliers, so that's why it is more desirable. And we computed errors where the errors really are dominated by the so-called population variance. So of course, when you have many data points, and you club them together, the statistical error on the mean or the median, whatever you're considering, goes down pretty quickly. But then you have to account for the sample variance from how much these spectra are changing from galaxy to galaxies, and this is the dominant source of noise for us. And already, if you look at the real data at redshift 3 and at redshift 2, you see that these two SEDs appear to be pretty different. And once we apply the code that we had to galaxies at redshift 3 and redshift 2, this is the picture that we found. Now the blue is redshift 3 and the black is redshift 2. I'm going to put the arrow time just to facilitate this. So we start from this one, for example. The amount of emitters of redshift 3 are essentially dust free. They have a little bit of dust later on. This is actually fair, something which is not unexpected. Bright galaxies will have dust if they are more evolved. Metallicity, they go from like strongly subsolar to actually solar-like. This seems like, too strong an evolution somehow in gigayear, but not so bad. The real problem here was this issue of the ages. So we found that it was like a pretty strong indication that the ages of galaxies at redshift 3 was around 1 gigayear, which is actually half the value of the age of the universe at that redshift. But later on, these galaxies appear to be much younger. And this, of course, means that if these samples are representative of the entire population, this excludes the fact that they can evolve into each other. And in general, it is a quite surprising result, just because, after all, if we want to think the Lehman condition represents something significant about the conditions, the environment, in which sort of condition does this happen, then it's hard to imagine that just 1 gigayear cosmological evolution means that Lehman condition is strongly suppressed at some point. So this galaxy, there is no overlap between these two samples of galaxies. So we started to look for reason why this could be wrong. One reason was like, for example, okay, maybe our data are not. And if you look at the SED and redshift 3, you do see that there are these points that are pretty scattered around. So we already did this with excluding these points and then excluding them in pairs. But still I found basically no difference. Another reason that I talked about is that perhaps my metallicity estimation is wrong. And this is just because, as I was saying, estimating metallicity from broadband photometry is actually a difficult business that I wouldn't myself trust too much as in being stronger than any indication. And this is something that can help, because age and metallicities are actually correlated, as you can see in these plots. In general, when there are diagonal axes of these ellipses, it means the parameters are correlated. And so if I can say, okay, the ages of LEs and redshift 3 are actually, so if I can move the metallicity down, up a little bit closer to solar, I would also obtain a younger estimate from the ages of redshift 3. And the opposite is true at redshift 2. So if actually the metallicity is overestimated, and I want to go down to values of solar or subsolar, I would obtain an estimate of the age, which is actually older, reconciling somehow this picture. So I try to run, like on both stacks of galaxies that I have, and an intermediate metallicity of 0.2 solar, which is more or less what we get from spectroscopic constraints for the few galaxies for which we have them. And you see that it helps a little bit, but not quite. Another thing that I thought was that, okay, That result was obtained for constant star formation history. We know that constant star formation history is obviously a simplification. So you could do a little better using an exponential either increasing or decreasing star formation history. At least you allow a little bit more freedom. Let's see if this changes the estimate of the age. And we didn't get anything like that. You can see these two distributions still far apart. And finally, I thought that this was actually the most promising, and I do still think that this is the most promising. I thought, okay, maybe there is more than one stellar population. And so in particular, I tried to rerun the code, assuming that a part of the mass is in an old stellar population, like an 8 gigayear-old stellar population. And I thought, okay, maybe also redshift 2. There are some old galaxies, but because their mass to luminosity ratio is so much higher, they're hidden. And so I just wanted to see if they came up. Or, perhaps what is happening at redshift 3 is that there are young galaxies and how in the stack they got washed away. So when I did this exercise, and here, what you see here is the age of the other stellar population, of course, the one that is assumed to be young. So redshift 2, nothing changes, but then, of course, what is interesting to look at is the ratio of the mass in the old stellar population with respect to the mass in the young stellar population. And you see it is constrained to be pretty small. So I don't see many on star redshift 2. On the other hand, you see here, this was kind of encouraging. At redshift 3, we saw now that these young ages are actually allowed. So I thought, okay, maybe this is promising, maybe there is a population. But then, if you look at when these young populations are allowed, is when basically all of the mass is in the old stellar population. So this doesn't seem to solve this problem. So we call this, I call this paper the curious case of Lyman alpha meters, because like Benjamin Butler, they seem to be getting younger with age. And I mean, my personal interpretation, I don't think that really what we're seeing is necessarily big results in terms of galaxy evolution. I think that this shows you the stacking is really, really dangerous. And I think the most promising thing that we can do is to study individual objects. This is actually what we're doing now with candles data. The candles data actually are particularly important because in this redshift they cover this near-infrared part of the spectrum, where as you can see the error bar is pretty big. And we cannot really hope to improve on IRAC, of course, especially on the 5.8 and 0.09 range, because they're not available anymore. So the near-infrared is where the Lyman break will be, and so hopefully this will help. And we already started with kind of guessing honor thesis. So hopefully that will bring some good and exciting insight on what was happening with these galaxies. All right, in the next few minutes, I want to talk about two of the
Go on. Just right. And this result we've seen, this is like the two galaxies we've seen. You're really selecting star-forming galaxies. That's what you're finding out. It's a common result, which usually the lower redshift. The star formation rate. Star formation occurs in lower mass galaxies.
Yeah.
So this result is consistent with that sense.
I mean, yeah, in terms of the mass, I agree with you. It's the ages that is kind of confusing. And you think that Lyman alpha is really strong in young stars, right? It's young stuff forming. So seeing all these like old ages is something really confusing.
The old ages at the higher redshift.
The old ages are higher. I mean, what is happening in redshift 2? It's actually, you would expect Lyman alpha meters to occupy the low mass end of the luminosity function. They're fairly young. A little bit of dust is okay, because anyway it could be like a dust geometry rather than mass doesn't need to be in the sheet. So I think it's just at a high redshift I don't understand.
Why are you getting those ages?
Yeah, and actually I looked at the literature, and even if there's like the nest that I have described, I think that many groups found that there are like a significant component of the old galaxies. And this is somehow counterintuitive. So I really would like to understand whether it just comes from the stacking, or there is like, can really old galaxies really start forming and not focus producing development?
CITA also one used in stardust from Earth.
Say it again?
If you have merging galaxies together, kind of big star, but you get what's line out for that you go.
That could be. Well, I mean, there has been, for that, I think you need the morphologies, and I think that, like, we have, well, not my group, but kind of the extended group of like. Well, so we are the people like Nick Bond had a proposal, and so, but we only managed to do like such high rushes anyway, and so we have HSC images of like maybe 5 or 6 of them. Steve Finkelstein has HSC's images. I think the rush is 4.4 of another handful. And actually we have been like jointly proposing, or actually I should say they have been jointly proposing to actually increase the sample size. Perhaps just because of this, just that morphology maybe will give you another handle, like this disturbed galaxies or what. But the numbers that we have so far are really, perhaps time for talking to us coming back.
What are the star formation?
Not very high, not very high. I think, like... Q2 is 10. Yeah. But again, the star formation that you get depends a lot on the star formation history that you assume.
But it's not hundreds.
It's not numbers, no. I mean, I'm trying to think whether we had something... No, I don't think, especially high ratio. In ratio 2, we have some which sort of have evidence for higher. And, of course, if you're getting old ages and if you're assuming that there is a continuous circulation rate somehow, there's no other, you're going to get those circulation rates.
You've got a funny selection. I mean, normally the generic star formation increases ratio 2.
Yes.
But you're particularly picking out higher alpha beta, so you're picking the higher star formation rate. But lower mass objects, I mean, you get higher alpha beta, so you can't have dust. So you can't have any old stars. So you gotta have a low mass. So you're picking out low mass star forming objects in calculations.
That is what we think, but there is something that is not consistent with this picture. It could be the assumption that we do. It could be, I don't know. It could be a selection effect that we're not aware of. I think the most likely thing is that the stack is not a good representation of the single galaxies that we are picking. I think that we are really mixing apples with non-apples. All right, so 2 things that I like to mention, and somehow these are application of seeing how try to use the code as a building block for new things. One of these is called MCMC. So I've been like talking about MCMC and how it's fast and how it's more efficient in exploring the parameter space. However, and so it actually, like when I optimize the code, like every iteration, like computing the likelihood that every step takes about 23 seconds. And when you're doing things like cosmology on large scale, you only have one universe, and you have to run chains in one universe. A few hours is not a big deal. But actually, with the galaxy service that we have in mind these days, we have millions, even millions of objects. So this is something that you actually cannot afford. So my idea for this was the following. So in parameter space, we actually build a grid. So this is the idea of the grid, but with a twist. But rather than saving the spectrum at each step, so at each coordinate of this grid, you actually just save the final vector of the fluxes that you obtain after performing all of the operations that I described at the beginning. So in the end, you just save a string of maybe 10 values which represent the fluxes obtained in each of the products that you have. And so some things will be fixed. In this case, for example, the assumption that you make in a stellar population model. The mass is kind of a free ride because it's just a normalization of each of the SDs. And this will be a function of the parameters that you change. So the grid will have a certain number of dimensions, which are the parameters that you vary. At this point, to actually explore the parameter space, you still do MCMC. So you're not confined to be on the corner, like when you build a grid and you approximate the probability distribution on the grid. You can still go inside, so you're not limited in resolution, and you still have all the good properties of MCMC, but at each point, to compute the spectrum, here for example, you just use linear interpolation, bilinear, trilinear, whatever you need to do. And this means that after you compute the grid, that will take still several hours if you have a certain number of parameter models. This is actually incredibly fast, and the computing time goes down by a factor of 10,000. So now if I wanted to do MCMC on a certain galaxy, it takes you a second rather than 4 hours. And so this makes the application to large galaxy survey actually a lot more doable. And of course, even if you're not limited by the spacing of the grid, so you can explore features of the probability distribution which are narrower than the spacing of your grid, you still want to make sure that your interpolation is accurate enough between different points. And so, but you see that these sort of numbers actually works well. You can determine that empirically. So this is actually really good for large surveys when you have many objects and somehow don't want to fix your assumption, the stellar population modeling once and for all, the filters are fixed and so on. But if you're investigating single objects or if you have many significant parameters, because I in particular don't know how to do a linear interpolation at the higher order than trilinear, I haven't been able to find a solution yet. So I actually would advise to use the original version of the code. And one thing that I'm actually applying to is data from candles. Candles, I guess you probably all know, but it's a cosmic acid linear interactive extragalactic legacy survey. Biggest survey ever conducted by the Hubble Space Telescope. The main things here is near infrared, is like YJH channels, but there's also ultraviolet and optical data in parallel. And the data become immediately also publicly available. So one of the things I like to do is to use this code to investigate from the point of view of the data which stellar population synthesis models actually work better. And there has been like huge debate in the community, for example, about the contribution of these TPAGB stars. And different data seem to say different things. Well, once you have like these large catalogs, you can actually say, okay, overall, is one, can I actually fit an empirical contribution and see if I find one that is best compatible with this large sample of galaxies? So this is one of the things that I like to do. The last thing that I want to mention, and yes, I promise I will stop after that, is something called galaxies, which is, up to now we have talked about what to do after you take the data. Well, this is something that you could do before taking the data and when you're doing survey design. So the idea here is that you will sometimes, for example, you're writing a proposal and you say, okay, I want to use HST and I want to measure stellar masses and I want to ask for 19 orbits because apparently with US plus 20 that's a big survey and nobody will approve your proposal. Okay, so given this constraint, what is the best things that I can do if I want to measure the stellar masses, for example? And of course, you can use a parameter estimation method. So you simulate the data, you can run Galaxy or your favorite SMB fitting code in a way. It is accurate and you obtain the constraints that you will have in each case. But because usually you want to try many different experimental configurations to find the best one, this may actually not be super convenient. Or you could use an approximation, which is the Fisher method approximation, which actually assumes that the likelihood is Gaussian, and then once you have made that assumption, basically the two pipelines are the same. Now, I've been saying the likelihood is no Gaussian, no Gaussian, no Gaussian, no Gaussian, so how can I say now that it's Gaussian? Well, I think in this case it's a trade-off, because the real problem, the real approximation, is that when you assume a fiducial model to say, oh, my galaxy data will look like that, this is a worse approximation than the one that you made in assuming that the likelihood is Gaussian. So before taking the data, this is almost the best that you can do anyway. And of course, this has the advantage that even if it's less accurate, it actually just takes a few seconds. And I won't go through the mathematics, but I'm sure that you are aware of what kind of approximation the Fisher methods assume. Basically, the probability distribution is Gaussian. So I stop at the second order in my expansion around the best fit or the highest likelihood. And we have done this exercise, and we have done it for at two different stages. The first one is with simulated data for various galaxy types. In this case, what we're really thinking, what we're really testing, is how bad the Gaussian approximation is. And in particular, in this case, we know that the Gaussian approximation for the likelihood always gives you optimistic error bars. So this is something to keep in mind. And we found that there is agreement within 20 to 30%. So this is not bad. And we've also done the exercise of computing. Well, we took like 500 galaxies and roots out, so these were real data. We applied MCMC acidic thinking, and then we did the same thing for the same, like typical, but simulated galaxies with the same parameters that we found here, and we obtained the constraints. And this is the difference. This is testing the fact itself that I'm simulating the data before taking them. So I'm assuming that my fiducial spectrum looks like something that I know. And here we found an agreement within a factor of 2. So it's not too bad. So, again, I wouldn't trust, I wouldn't trust anything like that once you have the data and you're analyzing it. But before taking the data, to get an order of magnitude that you can put in your proposal and it's reasonable, then I think it's fair. And I guess I wanted to show you how this works. This links work. So this is the website that we have. This data practices compute. And in this case, you say, okay, for example, I have, galaxies that are observed with this limited magnitude. You can say what type of gas this is. You can say which parameters you want to marginalize over, and you compute. I will tell you what kind of results you can expect to find. This is an approximation, but I think it's kind of very useful and neat things to have something very quick. So I would encourage you to use it if you think it could be interesting for you. All right, so my previous life, as you know, I did general relativity and tested general relativity with galaxies, and this is how I think they overlap. But I will spare you the details, and I'm here until Wednesday late afternoon. So if you're interested also in this part, you're always welcome to come talk to me. So what do I think are the interesting things to do in the field of acidic thinking? Well, first of all, this is again something I already mentioned. Theoretical models that we have do not agree with each other, and we need to understand better which one is right, if any. Stellar formation instances of galaxies that we use are far too simplistic, and I think in any case, all of them is a sort of parametric approach. You assume how many stellar population, and for each stellar population, you assume a certain functional form. It would be a lot better if we could do something different. Third problem, perhaps we should have put this at the very top of the list. I think that we are really evolving very fast in a situation where we are going to have so much data and not know what to do with it, and I think this is something that we should be thinking about. And then somehow it's related. I've been playing around with this machine learning and data mining techniques, and I think this is also something that, it's a young field, so I think it's fairly recent to be in this state, we have so many data and we don't know what to do with them, but I think that these are things that will be able to help. And then, of course, for me at least, I would like to test the concordance model of cosmology, in particular with HECTES and SST, which are collaboration with the I'm involved. And I'll stop here. Thank you very much. Yes.
So you were suggesting stacking the problem. Is there a reason you specifically think stacking would get you over the too massive or too old?
I think, well, I haven't looked in particular at how, this effect in particular can happen. But the problem with stacking is that if you take an STD, which is young and dust free like this, and an STD which is old and dust rich like this, and you put them together, what you get doesn't look like either of them. So, you see how easy it is to, and you can have a big error right here, which will tell you, okay, the stellar populations are different here, in fact, that don't really look alike, but still your average will be somewhere in the middle, which is something pretty undesirable. So you don't know that your stacked SED is a physical SED that looks like your typical galaxy there, just like matrix and everything. And because no property other than the mass independently as b linearly, then every time that you stack, you could be altering the properties of your spectrum. Yes?
So is it necessarily surprising the differences between the Z of 2 and Z of 3 LEs, given that kind of not only on the amount of dust in each, but also what the geometry of dust and outflows is in all of them? When we look at Z of 2 star-forming galaxies, then looking a lot on the young ones, you can see a lot of white malformation. Sometimes, because they're young, you've got a lot of star formation. And sometimes when you look at the old ones, you see a lot because those are the ones that have been able to blow out the gas and through a channel so you can see the white malformation that they have. And is that something that you think is separable?
No, I think that you are right. I mean, I still think that, we don't expect, given the same assumption, to find some sharp differences. And I think what we're saying here is that maybe the sharp difference is not really in the ages of the population, but in the dust geometry. But again, if they're only giga-year away, I wouldn't want them to look too different.
Right, but by the time you get to redshift 2, then you're starting to build up more of a substantial interstellar medium. You're building up more of a disk that isn't necessarily being blown out quite as hard as at redshift 3. So you might expect there to be some kind of a transition where, as you get down to redshift 2, then you're biased more towards the things that have the intensely high star formation rate that haven't necessarily been able to blow some out. And it might all logically be a difference.
Which will find a lower mass.
I will find a lower mass also.
The mass should probably affect it.
The mass?
Believe your masses.
Well, the masses are the one that it's really hard.
What's driving the mass? IR or?
I don't think, I think that we have a pretty good angle on the iron. And so I think that at that point, like a redshift 2 and 3, well, this means that we have like a good 1 micron stress strain. And I think that I can do. So, we have a good handle because we have like a fairly good, extended like wavelength range. And we have a pretty decent iron measurement, 3.6 and 4.5. So I tend to believe the masses. Given the uncertainties, given the systematics, but this of course wouldn't change from one redshift to the other. And I think if you look at the literature, I think that the masses are the things that we get more right. I don't know, but I agree with you, like in general, that talking about dust and ages, which are so different with each other, after assuming this like simplified version of dust, the dust geometry is very dangerous.
So how long does it take for the change to come here right now with the data that you have? Do you have to run it too long?
You mean numbers of steps?
Yeah.
It depends a lot on what models you use. So many people in this field use this so-called tau model, which I personally hate. And this is just because this is like an exponentially decreasing or increasing star formation. But if you vary like both the age and the tau parameters, well, these are really fairly degenerate with each other. The driving parameter is the ratio of the two, which tells you is this similar to the birth, is it like more constant, it is linear, somewhere in the middle, and so on. So for this tau model, which unfortunately I have to study, it takes like more than 100,000, just because you need to wait, and getting to the acceptance rate, it takes a little longer. But if not, I think the standard like few tens of thousands steps is alright.
So is this going to be a problem when you have a huge data set?
Well, if I have this with this PD version, not really. Okay, we go from like 1 second to 2 seconds, we do this.
And what did you use for the galaxies? What kind of technique?
Oh, the galaxies? Oh, well, the one that the online thing is JavaScript.
But the code itself?
Oh, it's got to be I know. It does have a Python wrapper, so I think you call it over executable with a Python wrapper. All that I could bring myself to do.
Alright, so let's thank you again, and we are going for